the matrix. Do you guys really want to know what this matrix thing is? Well, as we keep venturing down this rabbit trail, this rabbit hole, following the white rabbit, trying to figure out what this matrix is, you got the blue pill, you got the red pill. Which one do you want to take? The choice is yours. The choice is always yours. Okay. Now, matrices, as we're seeing, they are useful. They're very, very useful in lots of applications. We kind of touched on a little about some applications in terms of computer graphics, in which you can take a matrix and you can rotate pixels. But we did it maybe in terms of a unit box, but it's the same idea. And there are certain characteristics about some of these matrices we want to make sure that we preserve. Otherwise, the image will be distorted as you rotate things around the screen or around maybe a PNG, JPEG, or whatnot. So there's a lot going on. The more than meets the eye. It's still a phrase right there. Okay. So it might be very prudent for us then to really dig into what is this thing about the matrix, because as we're seeing, it's what happens with the matrix tells us some things about the solutions. And what we're after is we're after solutions. Why do I have them? And what can I say about them? And if I don't have them, what's the best case scenario that I can do? Okay. So first off, when we're talking about a matrix, a lot of terms here today, guys, but a matrix, you can think of it as really being a rectangular array of numbers. And if you're in computer science, you've seen rectangular arrays, maybe like linked lists. You see that quite a bit. So yeah, you can think of that as being a matrix. But for the most part, we're talking about things like something like 2, 3, 4, 1, let's say 5. Let's do that. 5, 6, 7, 8, 9, and then 11. Just to make your OCD go crazy because I didn't say 10. It's like, you should have said 10. I said 11 instead. Just remember, it's just really 10 plus 1. Okay, but anyways, there's your matrix right there. And we could talk about number of rows, number of columns. One interpretation, when I'm thinking about a matrix, yes, we can think of it in terms of the coefficients for the linear system of how we all orchestrate things. And then the rows we can consider as being the equations. And what goes in each one of those rows is the coefficients from the variables. And we could talk about, again, things like N by M. Just to kind of give you guys a refresher, where this refers to the number of rows, and this refers to the number of columns within the matrix. We have seen already, based upon given size, is what this is referred to as, the size of the matrix, certain characteristics are bound to happen. You just have to have it. Pigeonhole principle does play a role. Sometimes, though, when we're looking at a matrix, we're more concerned about what's called square matrices versus these rectangular matrices. And another term here, we say that a matrix is going to be a square matrix versus a round matrix. I don't know what a round matrix is, but we're talking about a square matrix. That's going to be N by M. And if it's understood that we're talking about a square matrix, sometimes we might just simply say the size of the matrix is N. Sometimes this will be designated right here, 3 by 3. Sometimes it may not. You might see something else. Okay. Now, with that said, we also at times might want to look at a whole entire collection of matrices. And for the most part in this course, we'll be talking about real matrices because, hey, we like to stay real with it. We don't want to be too complex. We don't want to go into the land of make-believe, imagination land, imaginary numbers. Stay real with the gang. So we might see things like this where we're talking about a set. We might say M by N, set of matrices of size M by M, whose values, let's say, come from complex field. Okay. If I really want to talk about complex field, I'll say maybe something like this. Or if I'm talking about the real field, maybe I want to really hit it home that, yeah, we are talking about real numbers. Maybe we'll do something like this to make some kind of alert to you, some kind of indication that we are talking about one numbers versus no numbers. And sometimes it is beneficial to talk about these so we can talk about these. Okay? Because remember, all real numbers, they are a type of complex number, It's just the imaginary piece for the complex numbers of a plus bi. It zeroes out. Okay, now, also we might just say mn. That's going to indicate that we are talking about square matrices of size n. And I could say this, or I might just leave it off and just know the context what we're talking about. We're more likely to be talking about real numbers. Okay. Now, with that said, there are a lot of characteristics with matrices that we definitely do need to be mindful of. And when we see these patterns, we can jump on the patterns, which will really help us in our calculations. When we're talking about matrices, I want to label the addresses, like an address in a program, where you have memory that goes into certain locations. Well, I want to label the address, the entries in the matrix, so I know it goes in certain locations. Oftentimes, if I was to say, like, this is matrix A, we could do something of the form where I can say that this is going to be A1, A2, A3. But that's confusing because when I come down here, if I say A1, A2, A3, and then do the same thing, okay, we're going to run into a big problem very quickly because that's saying that all the variables are the same. And that's probably not the case. And I probably don't want to say A, B, and C because eventually I got to sing the alphabet song to myself and I'm going to forget. We're going to go to 26 letters and maybe 28 if I borrow another language, but eventually, okay, I'm going to crash and burn very quickly. The way that we typically designate the different locations is we'll say things like 1, 1, 2, 1, 3, where if I have ANM, this entry typically refers to the index for the row. The next entry typically refers to the index for the column. So if I say 2, 1, that means I'm in the second row, first column. 2, 2, second row, second column, and also 2, 3. And just follow the scheme. 3, 1, 3, 2, 3, 3. And I can chase this all the way down. Okay. Now, this, whenever I have a matrix A, it does not mean that lowercase letters are automatically assigned to the matrix A. Typically, we mean that, but you do have to define it when you're going through your problem. So you got to be careful. Just think like when you're writing a computer program, you have to define your variables, because if you don't define your variables and you use them in a calculation, what happens to your program? Crash and burn. Compiler doesn't work. And you're going to spend 5 hours wondering, how come my code doesn't work? Because of one semicolon. Oh, I hate that, but it does happen. Okay, so here's matrix A. And another way that we can denote this would be something like A with the brackets, like IJ. And you'll see this IJ oftentimes they indicate that we are talking about the dimensional entries. Within the matrix, no, red pill, blue pill kind of thing. Within the matrix, if you were to go along this direction, down this, that's your diagonal. And there's lots of characteristics with the diagonal of a matrix that we want to make sure that we're mindful of. And I might want to designate it. I might say dag A, which just means I'm talking about the diagonal of a matrix. And this is just going to refer to A11, A22, dot, 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 all the way up to ANN if I'm talking about a size n matrix. I usually don't want to talk about the diagonal entries if it's not a square matrix. I could, but a lot of times we are focusing on square matrices, as we'll see as we keep venturing further and further down this rabbit hole that we're going down. Okay. Now, up here, you have what are called the upper or lower entries off the diagonal, so your off-diagonal entries. And sometimes when you're going through your calculations, you're going to run situations in which all these entries up here, they're all going to zero out. Okay, you might have a matrix which has this particular form. Doesn't matter what happens down here, but what happens up here. Or you might have a situation in which you have all the entries above, the main diagonal, that's what the diagonal is again. They might be some values, maybe something like this, but everything below it is all going to zero out. Now, these matrices have a special name. Either you have this case, or if you were to have this case. These are known as your lower triangular matrices. And please note, it's not matrices, it's matrices. A little different. You don't just tack on an S at the end. Okay, here, these are known as your upper triangular matrices. And there are certain characteristics that we're going to explore about when I see these patterns, it's going to allow me to do a calculation that fast. Okay. Now, the intersection, when you look at your lower, you look at your upper, right smack dab in the middle, right here, are matrices which are both upper and lower. So maybe something like this. In those matrices, these are known as your diagonal matrices. We're really just focusing on the diagonal entries within the matrix. And these matrices, they're also really important. There's a lot of characteristics with them. And that really just talks about lots of different flavors, lots of different types of matrices, different classifications that we're going to see. One classification that we have already seen was the identity matrix, typically denoted as I sub n. And if you're doing a little bit of programming, maybe in MATLAB, you might run into I, where you are talking about the identity matrix. And in different programming languages, mathematical programming languages like maybe Maple or Mathematica, you're going to have some kind of protocol, some kind of function call, to which you maybe would call up the identity matrix. Again, all this refers to is it's a matrix of the form. We can say it's 3 by 3, 4 by 4, 2 by 2. It doesn't really matter. But it's going to look just like this, where everything along the diagonals is going to be 1 and everything else is going to be 0. You can also think about it in terms of the standard basis vectors. Here's E1, here's E2, here's E3, and we get the E4, take an E walk, and there it is. Okay, so you can think of it from this perspective. And sometimes, guys, it will be very, very helpful when we look at a matrix in terms of its column vectors, like that. There are going to be times in which I might want to look at it in terms of what's called as row vectors. And row vectors just means I'm looking at it in rows, as the name would suggest. A lot of times when you're looking at definitions, I know it can make your head spin. You're like, I'm not sure what's going on. But the meaning is imbued within the term itself. That's why we don't call it the hippopotamus property. I'm still in favor of calling everything the hippopotamus property because I just like that word, hippopotamus. Do you guys know they have a hippopotamus day? Great day to celebrate math, right? Hip hip hooray, hippopotamus. But if you see something that talks about rows, we're talking about rows. If you see something talking about columns, we're talking about columns. And if we're seeing things which, like fractions, we're talking about things which are broken. That's what a fraction means. When you think of the word integer, it comes from the whole entire root word. We get the word from integrity from. Integrity? Integers? And when your integrity, when it's broken, it's called a fraction. A lot of times when you see terms, the meaning is really imbued within the term itself. And we see that in terms of linear independence, linearly dependence. We're seeing all kinds of things like that. Okay? But the identity matrix and the diagonal matrix, these are special matrices that we're going to run into. From time to time, we'll talk about the all zero matrix. Zero matrix, where every single entry within it is a bunch of zeros. And this could be a n by m. Doesn't have to just be a square matrix. And we might make it a little bit more fancier and put a little loop on it, because loops are kind of cool sometimes. And we might also just designate it like this, or you might designate it like this, or you might just say this, or you might say this. So again, you have to know the context of the problem. If it's confounding what we're talking about, we might not want to do that. It might be better just to say this. Okay. So you'll see this notation from time to time. And there's also another notation. It is J. What's J? It's the all ones matrix, where every entry is just going to be 1. Now, there's some really important things about the all one matrix. And if you do some things maybe in data science, you'll see this pop up from time to time. Okay. So with matrices, there's lots of operations. And we can talk about what's called a binary operator. Like what? Binary what? Well, a binary operator, what it means is you operate on two things, hence binary operator. Two things come together to form one. We can talk about if I was to have a matrix, let's say 1, 2, 3, 4, add to another matrix, 3, 4, 5, and then 7. Because didn't want to say 6 again, because you'd be like, why not? But 6 plus 1 is 7. Just think like that if you need to. But if you add up your matrices, here's the secret. Shh, don't tell people. You add up component-wise. First component with first component, second component with second component, this component with this one, and this one with that one. That's the sum of these two matrices. Why is that the case? Well, remember, if you think about a matrix in terms of the coefficient matrix of a linear system, and if you were to have x1 plus 2x2, and let's just say equals a value of 3, argument's sake, and if you had this one over here, you had 3x1, you had 4x2, let's say equals 5. If you were to take these two equations and add them up, how would you do it? Would you take the x1 and add it to the x2? No. You add it to like terms. So you take this x1, add it to that x1. So why do I add up component-wise? In a sense, I'm adding up these like terms. First component with first, second with second, third with third, fourth with fourth, so on and so forth. Okay. With that said, let's say if you were to have 1, 2, 3, 4, 5, 6, and you're going to add it to 1, 2, 4, and 7. Just to really jumble it up this time. First component with first component, second with second. But wait a second. What do I do with these? We have a mismatch of dimensions. This is a 2 by 3 matrix. This is a 2 by 2 matrix. You cannot take a 2 by 3, add it to a 2 by 2. That's a problem. Now, you might think, well, what if we just put in zeros, so it zeros out the column so I can? Okay, you might do that stuff in physics. It's pretty heavy over there in the physics department. The gravity of the situation, But when we're talking about matrices, we're talking about making sure we're in the dimension that we're working in. This is actually exists in a certain dimension. This also exists in a certain dimension in its own self. And you're thinking, what do you mean? Well, we're going to have to find out in a few weeks what I mean about this being in different dimensions. So here's the deal. If you want to add up matrices, they must be conformable. In other words, they must have the exact same size. Game over otherwise. You can't do it. It's not defined. So make sure that these match. Okay. Now, with that said, you can also talk about taking the difference of your matrices. You can also have another binary operator in which you're taking two matrices and you're multiplying them together. If you look at perhaps 1, 2, 3, 4, and let's say 1, 0, minus 1, 2. So if I was to multiply it out, I would do it pretty much the exact same way that we have been multiplying out everything so far. But before I do that, let me just back up a little bit. And let's go back to this one. And let's say 0, 2. Remember how we're working through these systems where we had a matrix that operates on a vector? I can think about taking the vector and rotating it around in the second dimension. Maybe I'll rotate it or stretch it, skew it, or whatever I want to do. That's how at least I can think of a matrix. Again, take this entry, multiply it by that entry, and then 2 times minus 1. Do the same thing down here. And then clean up the results. So we have 1, minus 2, minus 1, 3, minus 4, minus 1. Here, do exactly the same thing. Take the row with the column, and in calculus 3, we would say, compute the dot product. Guys, that's all it is. Take the row, dot it with a column. These entries multiply together, these entries multiply together, add up the results. Same thing, 3 and 0, 4 and 2. Now, if I was to look at the matrix 1, 2, 3, 4, and 1 minus 1, 0, 2, the way that this works is the exact same way. Take the matrix, take the row, dot it with a column. And that entry will go right there. Take the row, dot it with this column, and then that entry goes right there. So based upon which column you're dotting, it's going to tell you which column you're going to put it in. And if you move down a row, you're going to move down a row and do the process all over again. It's like it's an algorithm, isn't it? It's like you're programming something in. Huh. Take the row, dot with the first column, it goes here. Take this, put it here. And what you get is you're going to get the vector -1, -1, 4, 8. It's the exact same thing. So that does kind of unlock a secret when you're multiplying matrices. If you have a matrix AB, you can think of a matrix again in terms of its columns, and sometimes it's very helpful to do so. We have column 1, column 2, column 3, as many columns as you want. As many as I want? Well, yeah. And when you operate, what you're doing really is you're operating on each one of these columns, and you're seeing what happens under the transformation. That is, in a sense, is what matrix multiplication really is. A whole bunch of vector operations in a single step. Okay, now, with that said, you can take as many columns as you want. That's fine. But you have to make sure when you're operating on the vectors, they're in the right space in order for this to work out. If you were to have a matrix A, which is, let's say it's going to be an n by 3, matrix B, which is going to be a 3 by 5, this will work out fine because your domain talks about the number of columns. That's what that is. So you're taking something from the third dimension, and then you're going to operate on the vector, or excuse me, the matrix A, and do something with it. And what happens is, as long as the rows and the columns, they are identical, then it will be defined. The matrix you'll get out of it, matrix C, is going to be a 2 by 5. Or in more general form, if you have an n by m, m by, I don't know, t, take those, throw them away. The matrix size is going to be n by t. If these are not the same, you can't work it. So let's say if I gave you the matrix 1, 2, 3, 1, 0, 1, and I gave you 2, 1, 3, 4. How would you work this one? This is a 2 by 3 matrix. This is a 2 by 2 matrix. Sorry, guys. You can't do it. If you take the third dimensional vector and you try to dot it with a two-dimensional vector, catastrophic results. Not going to happen. You can do this with this, that with that, but what do you do with this? Okay, that's not going to work. But let's say if you have 2, 1, 3, 4, and you have 1, 2, 3, and then 1, 0, 1. This is a 2 by 2. That's a 2 by 3. This will work because these match up. And again, the way that I would do it, take the row, dot it with a column. Take the row, dot it with a column. Take the row, dot it with a column. Take the row, second row, sum in the second row now. Dot it with the first column, sum in the first column. And then for the second column. And then lastly, for the last column. There's a lot of information that's being played out right now. And one of the things is this. Here I had a matrix A, and I had a matrix B. Call this A if you like. Call this matrix B. I couldn't do this. But I can do this. What does that say very quickly? They're not the same. So everything we've been so accustomed to, of commutativity, you just throw it out the window now. Oh no. Oh no, no, no. I don't like this. I love my commutativity. Is it time to go back inside the matrix? I really don't want to go outside of it. Why did I have to take that pill? I didn't want to. Too late. Let's say if you have this matrix, 0, 1, 0, 0. And just like with numbers, I can talk about powering up a matrix. I can power up the second power. And that just means take the matrix, write it out twice, go through the whole entire process, dot the row with a column. So this with that, this with that, this with that, and then this with that. What just happened? My world crumbled. It shattered. No! I took two non-zero matrices. I multiplied them together, and I got a zero matrix. So something that we love, it was the whole entire zero factor property. I love that property. It's gone now. I didn't realize how much I loved it. Because when I'm solving polynomials, I would first factor it, and then set equal to 0, and then solve. It was great. Those days are gone. Oh. Sometimes you will not have the 0 factor property. So if you have AB equals 0, it does not mean that A has to be 0 or B has to be 0. Things fall apart very, very quickly. Do you guys sure you want to know about this matrix stuff? Why are you here? Now, with that said, there are different operators, and a different operator is, we often talk about binary operators, putting two things together to form one thing. But I can talk about not just operating on one or two matrices, I can talk about operating on one matrix by itself. And one such operator is known as the transpose. I can designate it with a lowercase t, I can designate it with a capital T, I can designate it even with a capital H if I'm talking about what's called Hermitian matrices. And that gets a little bit complex because we're talking about complex numbers then. We can talk about what's called a conjugate star operator. And all that means is when I take a matrix, take the conjugate star, take the complex conjugated numbers, and then transpose it. Okay. The way that it works is basically get a nil, look along the diagonal, right here, put it in the board, and then pivot. A row became a column. Take another nil, put it right there. Pivot. A row became a column. The only thing that stayed in place is where you pivot. Like if you're going to put a board up and you put one nil in it, you're pivoting. Okay, now, the way we're going to pivot, we pivot down this way. And I can do this with 2x3s, I can do it with 2x2s, I can do it with 4x4s, but you might need a really big long nil for a 4x4, right? If you were to have, let's say, a 3x3, and you take the transpose, take the row, make it into a column. Then take the next row, twist it, turn it, bob it. Then hold what you got, get your column. Do it for the next one. Put a nil right there, pivot. Whoa, that's crazy. So I'm operating on one matrix, not two of them, and I get something new. And one more operator here is something called the trace. The trace is really going to be defined when we're talking about square matrices. And this is something that, yeah, you're going to need to know too. So if I have a 2x3, sorry, Charlie, hope no one names Charlie, you're out of luck. But if you have a 3x3, you can do this. The trace operator, it's defined to be the sum of the diagonal entries. In more general terms, if you take the trace of a matrix, you sum the diagonal entries. Now, there's consequences of doing so, and we're going to see why this is so important. And there's some other operators we can talk about as we keep pressing forth. So we got kind of a good idea, what's going to happen if you were to take a matrix and, add them together, or if you take a matrix and you're going to multiply them together. And we can also talk about if you were to take a matrix and scale it, if you were to have, let's say, 2, 4, 0, 5, if you multiply it by 3, that's really saying you're taking the matrix 3 times, adding to itself 3 times here. First component with first, second with second, third with third, fourth with fourth. And what that amounts to is 3 times 2, 3 times 4, 3 times 0, and then 3 times 5. So in other words, when you scale a matrix, you scale every single entry within the matrix to get your other new matrix. Addition we got, scalings we got, multiplication we got, crazy transpose we got, crazy trace. How do you divide matrices? I don't know. I don't want to go there. That seems too crazy. Is there a way out? Can I leave right away? Because this is getting crazy. I love the commutativity. I love the zero factor property. I don't got it anymore. Who made up this linear algebra stuff? Oh, man. Too late. Too late. All right, guys. This is all the time we got for today. You have a great day. I'll see you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.